Okay, so now that I've started the recording, you can type your name into the chat and I'll have a record of it for your data. If you typed your name in already, those names will be lost. So please type your name in again because the chat is only saved from when I start recording, not from before. So even Abraham, Theophilus, Robert, Harrison, Omasco, all of you can type your name in one more time, and then I'll have the record for your attendance. Okay, so welcome everyone. I hope you all had a good week. Thank you again for showing up punctually, and looking forward to starting a new unit for what we're doing. So we're going to finish what we were going to do with geometry. It's really just a little taste of geometry. I wanted to emphasize, a couple of points about, triangles being fundamental and about in mensuration, what formulas look like. So we'll go over a few examples from geometry for the first half of class today. And then I want to move on to the second half of class, which we're going to go back to algebra and we're going to talk about word problems specifically and what are some good hints for teaching them. All right, so good evening, Christian. So first, let me just review, recall what we talked about last time is that we talked about the centrality of triangles to plane geometry, that lots and lots of questions in plane geometry can be reduced to triangles. And we saw that one of the reasons for this, and this is something that we'll see in the homework, is that every polygon can be triangulated. So you can always break a polygon up into triangles, and often you can gain insight into its area or other properties of it by breaking it up into triangles. And so what we said is that in general, it's difficult to memorize formulas involving polygons with lots of sides. Like nobody knows the formula for the area of an octagon, right? It's just not a formula that's easy to know. But if you break everything up into triangles, which are simpler, then you can use what you do know about triangles in order to solve problems. Okay, so I do want to go over the homework. I think I only got one homework solution sent to me from James, and that was sent pretty recently, so I didn't really get to look at it. So let's go over these homework problems. So this homework exercise one, which had a diagram. So what is the area of the segment of the circle of radius 3 shown below? So let me redraw this diagram. We have a circle here, and I had an arc over here, and the circle was radius 3, and the segment that we want is exactly this area right here. Okay, and the arc over here is 90 degrees, which means it's 1/4 of the circle, 1/4 of the circumference. Okay, so I received one solution of it. From looking at it quickly, it looks like it's correct, but the hint here is, can we add a triangle? So can we add a triangle? Whoa, what just happened here? Why? Oh no, here we are. Yeah. So can we add a triangle somewhere in this diagram so that we can make a portion of the circle whose area we do know how to calculate? Okay. So does anybody want to help me for how to do this question? Okay. So I mean, maybe this is hard to discuss over Zoom, but the idea for this is that you can draw in another triangle here. I'm going to draw this triangle in red. So if you throw in, and this is generally what you want to do when you have a segment of a circle type problem. So I'm going to draw this triangle over here in red. And the idea is if we can calculate the red area and we can calculate the combined red and blue area, then we can calculate the blue area, right? So what we want is the blue area. And so what do we know? Well, the red area is what? Well, this is a triangle, right? And it's a triangle. This is the center of the circle over here, right? It's a triangle where we know that these sides of the triangle are radii of the circle, right? So these have to have length 3, just like the radius of the circle, right? So this has radius 3, or this has length 3, and this has length 3. And then we also know that this arc is 90 degrees. And what is the definition of the degree measure of an arc? It's exactly the size of the central angle that cuts it off, right? So that tells you that this angle here is actually a 90-degree angle, or in other words, a right angle. Okay, so I've drawn the little right angle sign there. So you have a right triangle where this side has length 3 and this side has length 3, right? So the area of the triangle is going to be what? So does anybody want to tell me what the red area has to be if you've got a right triangle where the two legs are both of length 3?
It'll be now
9. Okay, so how do we get that?
you times 3.
Right, exactly. So 3 times 3, but remember it's a triangle, not a square, right? So we do 3 times 3. After that, what do we have to do? We have to divide it by 2, right? Because the area of the triangle is 1/2 base times the height, not just the base times the height, right? So it's going to be 3 here, right, is the base, and this 3 here is the height. And so when we multiply them together, you get base times height, but the area of a triangle is 1/2 base times height, right? So this is going to be 1/2 3 times 3, or if you want to simplify it, this becomes 9/2. Okay, great. So the red area is 9/2. So now what else do we know? So what else do we know? We know that the blue area plus the red area. Well, what do we know about the blue area plus the red area? Well, if we look at this, this is 90 degrees. That's a quarter of the circle, right? So that's a quarter of the circle. So that means whatever this combined red and blue area is, it's 1/4 of the area of the circle. And this is a circle of radius 3, right? So this red area plus red area equals 1/4 times the area of the circle. And 1/4 of the area of the circle is 1/4 times what's the formula for the area of the circle? Well, it's pi times the radius squared, right? Because this is pi times, I'll put it in green, it's pi r squared, right? That's the formula for the area of a circle. And simplifying that furthermore, this gives us, so this is going to give us 9/4 pi. Okay, when you multiply this all out, right? Because you get 3 squared is 9 divided by 4. So the red area is 9/2, and the red area plus the blue area combined is 9/4 pi. And so if you want to just know the blue area, so the blue area equals, well, I'll say red plus blue area minus the red area, right? So the blue area is equal, if you can do all of the red plus the blue and then you subtract off the red, then it's the red plus the blue area minus the red area. We already know what the red plus the blue area is. We figured that out. It's 9/4 pi. And then minus the red area over here, so that's 9/2. And so that's the final answer. And if you want to simplify it by pulling out a 9, you can. It's not very important. You could write this as 9 times 1/4 pi minus 1/2. And you can leave this as the answer. Okay, so the key here is that we don't have a formula for the area of a segment. That's what this part of a circle here is called. It's called a segment. And we don't have a formula for the area of a segment, but we can write it in terms of things that we do know the area of. One of which is a triangle, which is our main topic here. So we know what the area of a triangle is. It's especially a right triangle like this, where the sides are just 3 and 3. And then we also know the area of any fraction of a circle, right? Because we know that, we know the area of a circle. And so if you've got a quarter of a circle, then the area is 1/4 the area of the entire circle. So if you take this big area, which is the quarter circle, and subtract off the area of the triangle, then what you're left with is the blue area, which is what the question asks for. All right. Any questions on this?
Hello,
Uh, yes, Rush.
hello.
Hello.
Just come
Yes.
because the internet gave me 12 time to come in. Yeah.
Okay. Yeah, you're coming in.
Yeah.
Question?
You get me? Hello?
Hello. Yes. Yes. I'm getting you.
Yes, yes. For me, I just coming in because the internet gave me 12 time to
Oh,
come
okay. Okay.
in. I don't
All right. Well, we,
I
we
don't know what
haven't done very much. That's fine. We just have
okay.
we just have the first homework exercise. Okay. Welcome. Okay. So there's no questions on this. We'll move to the next one. So the next one says we're given a rectangle with a whole bunch of measurements. So again, it's worth it to just draw it. I'm going to just draw this rectangle here. This is A, B, C, D. This measures 18. We have a point M here. This is 12. This is 12. Okay, and then I'm going to draw this line here from M to E. Somebody just came in. Okay, line here from M to E, and then DE is going to be equal to X. And the goal is we want to find the value of X so that the area of region AMED is exactly twice that of region MBCE, right? So we have this region over here. This is AMED. It's the region on the left. And we have region MBCE. It's this region on the right. And we want to do this without using the area formula for a trapezoid, okay? And so the hint is we want to draw appropriate lines to divide the regions into triangles and rectangles, right? Because triangles and rectangles are easier formulas to use. Okay? So does someone want to tell me what lines I should draw? Ideally, right, we're going to get an expression for this area in terms of x, and we're going to get an expression for this area in terms of x. And so in order to do that, if we want to break it into triangles and rectangles, what line should I draw to be able to do this? Anybody?
Please come again.
Yeah, so what lines should we draw to divide this figure into triangles and rectangles that will make it easier to calculate the area? Well, okay, well, I'll draw a line. Basically, what you want to do is just draw straight lines. So you've got these trapezoids, but a trapezoid can be reduced to a triangle and a rectangle just by drawing a line like this. So if we draw these two vertical lines here, okay, then what we see is that this region over here has two pieces. One is a rectangle, one's a triangle. And this region over here has two pieces. One is a rectangle, one is a triangle. Okay? And what we should do is calculate what the area of each region is, right? So what's the area of AMED is equal to what? Well, we need to do the two pieces, right? So we have a first piece here. This is a rectangle. Its length is 12, and its width is, or its whatever you want to call it, height is 18. So the area over here, I'll use green for areas, area equals 18 by 12, right? So whatever that is, that's 216. That's this piece. So now, what about this triangle over here? This would be the next one to do, is this triangle. Triangle ME. I mean, I can give this point a name. I could call it F if I want. MEF. Okay. Well, we know that its height is 18 and its width or its base is what? Well, the entire base here is X, but this part over here is 12, right? Because it's opposite this 12. So that means what you have left here is X, but minus 12, right? So this here is going to be X minus 12, right? If we put this up, it's going to be X minus 12. And so that means that its area from the area formula of a triangle is going to be 1/2 times the base, which is X minus 12, times the height, which is 18. Okay, so I'm not going to simplify that right now. Okay, so the area of AMED is going to be 216 plus 1/2 times X minus 12 times 18, or in other words, 216 plus 9 times X minus 12. Okay? Right, because just 1/2 times 18 is 9. Okay, so 216 plus 9 times X minus 12. Okay. Any questions about this part so far? Right, ultimately, we're trying to compare the region AMED to the region MBCE. So we want to find an expression for both areas. And then once we have an expression for both areas, we can set one equal to twice the other. Right, so any questions about area of AMED? Good. Okay. All right. So what do we have over here? Well, we need to figure out what these lengths are over here. Well, we know that AB is 24, right? Because, oh, sorry, this AM equals MB equals 12. That's a misprint. AM equals MB equals 12. Okay, so we know that the entire long side of the rectangle is 24, right? So that means if this over here is X, then what's left over here has to be X less than 24, right? So this over here is going to be 24 minus X. Right? It's going to be 24 minus X. right? Because they have to add up to 24. So if you've got x, you have to have 24 minus x. So that means this rectangle here is going to be um, height of 18 and a width of 24 minus x. So this area here is going to be 18 times 24 minus x, right? That's going to be its area. Now, what about this over here? Again, we have a height of 18, but what is this? Well, we know that MB is 12, and this here is 12 minus is 24 minus x, right? So if this is so if this entire thing is 12, and then this length right here is 24 minus x, then what you have over here is going to be 12 minus 24 minus x. So this is going to be, I don't want to clutter the diagram so much, but let me call this point G. We're going to have that, that mg is going to be 12 minus 24 minus x. So let me write this out here. We're going to be doing the area first, before I do the area of MBCE, I'm going to have that the length of mg is equal to 12 minus 24 minus x. And this, when you simplify it out, this becomes 12 minus 24 plus x, which becomes x minus 12. Okay? And so what that means this area is going to be is it's going to be the height, which is 18 times the width, which is, well, actually, maybe I'll write 1/2 first. So it's a triangle. So it's going to be 1/2 times the base, which is x minus 12, times the height, which is 18. Okay? Or, right, of course, we could have also just seen that these two triangles are equal to each other. So they have to have the same area, right? These two triangles are congruent to each other. But regardless, we figured this out on its own if we needed to. Okay, so this means now that the area of MBCE is what? Well, it's the two pieces together. This first piece is again 9 times x minus 12, 9 times x minus 12, and now you have to add 18 times 24 minus x. So plus 18 times 24 minus x. Okay, so we have 26 plus 9 times x minus 12, and on the other side we have 9 times x minus 12 plus 18, 24 minus x. So now what do we want to do? Well, the question says, what should x be so that this area is twice as much as this area? So we have to take this first area over here and set it equal to twice as much as the other area, right? So our equation is going to be 216 plus 9x minus 12 is going to be equal to 2 times 9x minus 12 plus 18, 24 minus x. Right, so this is the equation, and the goal is to solve for x, right? We want to find the value of x that makes the left region twice the right region. So now that we have this equation, we're going to solve it for x. So before we go ahead and solve this for x, are there any questions of how we got to this point? How do we get to the point where we set up this equation? We're just trying to write down what all of the different areas are in terms of triangles and rectangles so that we can compare them. So any questions on this so far? Okay. All right, so let's just solve the equation to be complete. I had a page for diagrams for homework exercises, but let's just solve the equation. I'm just going to rewrite it from last time. So we have 216 plus 9 times x minus 12. So 216 plus 9 times x minus 12 equals 2 times 9 times x minus 12 plus 18 times 24 minus x. All right, so let's just solve it. I'll keep the 9 times x minus 12. I'm not going to simplify that out yet. I'll distribute the 2 over here. So this gives us 18 times x minus 12 plus 36 times 24 minus x, because it's got to be 2 times that. And so now I'll subtract the 9 times x minus 12 from both sides. So minus 9 times x minus 12 and minus 9 times x minus 12. So this is going to give us 216 equals 9 times x minus 12 plus 36 times 24 minus x. And at this point, I'll actually simplify everything out. So this gives me 216 equals 9x minus 108. That's 9 times 12. And then plus 36 times 24 is, so 36 times 25 would be 900. So you got to subtract that. So that would be 864 minus 36x. And that is equal to, combining the 108 and the 864, that would be 756, and then 9x minus 36x, so 756 minus 27x. Right, x equals 20. Yeah, this seems right. Yeah, that's good. So let's just solve this, right? So this gives us 27x equals 756 minus 216, which is equal to 540. And then we can divide by 27 and divide by 27, and we end up getting that x is equal to 20. Okay. All right, so x is equal to 20 when we solve this equation. And we should, if we look at the diagram, that kind of makes sense, right? If x is equal to 20, that means that this line is going most of the way towards c, right? Because the total side is 24. And if x is equal to 20, that means this is 20 and this is only 4. So that looks at the very least like it makes sense. And we can check the answer, which I'm not going to do right now just for time. But you should check the answer. Check that when you plug in x equals 20 over here, that if you calculate this area, what is this? 216 plus, if you do 20, you're going to get 72. So this area is going to be 288. And this area here, when you plug in 20, you're going to have 72 and 72, which is going to be 144. So that's exactly right. You're going to get 288 and you're going to get 144. Okay? So that's how to do this. There's other ways of doing this. For instance, if you wanted to simplify it, you could show that the entire area of the rectangle is 24 times 18. And so what you really want is to just get this area to be 2/3 of that. Then it will be twice the remaining area. So you could do, 24 times 18 is 432. And so you could say that what you actually want is for this area to be 2/3 of 432, and then do a calculation there. It makes the algebra a little bit easier. But I think it's nice to just do the problem directly without anything clever, without any shortcuts, just doing exactly what the problem says. It says you want one region to have area twice as much as the other region. So you calculate both areas in terms of a variable, and then you solve for that variable. Okay? So any questions? Any questions about this homework problem? How we do this derivation? No questions? Okay. All right. No questions, then we will move on. Okay. Um, all right, give me a second. Okay.
Hello.
Yes, question?
Yeah, Rush.
Yes, Rush.
In case that like maybe want to do it like or saying divide both sides by 9.
Mm-hmm. Yeah, you could do that. If you wanted to just replace this 18 over here with a 2 to divide both sides by 9, it wouldn't affect the problem. Or over here, like once you have this equation, if you want to divide both sides by 9 to simplify it, yeah, that would be fine. That might make it a little easier to solve. Yeah, that's
Oh,
completely fine.
okay.
Okay. Yeah. Any other questions? Okay, so let's move on. All right, so I got a question last week about the area of a triangle in terms of the circumcircle. So I wanted to take a little bit of time to do that. So I forgot who asked me, but somebody asked me a question about this last week. So, so one of the things is that we should recall from last week is that we proved that the area of a triangle, one of the formulas you could have was RS, where R is the radius of the inscribed circle and S was the semiperimeter. And in fact, we show that this formula is true for any polygon with an inscribed circle at all. Okay, so it doesn't have to be a triangle. It could be a polygon with any number of sides. As long as it has an inscribed circle, then the area is this exact same formula. It's RS, radius times semiperimeter. Okay, and I just want to warn you though that this is not all polygons. For instance, a rectangle usually will not have an inscribed circle. In fact, it only has an inscribed circle if it's a square. Okay. Right, because if you I mean look at this, right? If you try to take a rectangle and you try to inscribe a circle, it's just not going to work because if you want it to be tangent to these sides, it's a circle. It's just not going to stretch out wide enough to hit the other two sides. Right? So this rectangle, you can't use this formula because it doesn't have an inscribed circle. So maybe I'll say this is no good. Does not have an inscribed circle. But if your polygon does have an inscribed circle, then you can use this RS as a formula. So there was a request last time to derive the formula for the area of a triangle involving the circumradius. So it turns out there's another formula for the area of a triangle, which is ABC divided by 4R. Okay, and here A, B, and C are the sides of the triangle, and R is the radius of the circumscribed circle. So I'll just give a diagram. So if this is A, B, and C, then you have your circumscribed circle that goes around the triangle, and it's got a center, and that radius is R. Okay, so it's the radius of the circle that passes through all 3 points of the triangle. Okay. So it turns out this is a formula for the area of a triangle, and it's not such an intuitive formula. But one thing, and I'm going to prove it to you, that the proof isn't that hard. But one thing I want to do before I prove it is to just convince you that this formula makes sense, right? So remember what we talked about 2 classes ago, 2 weeks ago, which is that if you have an area formula, an area is a two-dimensional formula, which means that any formula you have for area, if you multiply all of the length inputs by some constant, then the area should get multiplied by the square of that constant, right? This is what we had 2 weeks ago. So we're saying if we multiply all of the length inputs by d, then the area formula should get multiplied by d squared. So before we prove this formula, let's check that it could possibly work. Okay, it has to satisfy this rule that all area formulas satisfy, no matter what the shape is. All area formulas satisfy. If you multiply the length inputs by d, then the formula has to get multiplied by d squared. So let's try it out. What are our length inputs? Well, A, B, and C are lengths. They're the lengths of sides of the triangle. And R is also a length because it's the length of the circumradius, right? So all A, B, C, and R are all lengths. So let's see what happens when we multiply them all by D. I'm just going to check. I'm going to add this on a new page. So check what happens to ABC over 4R when we just multiply everything by D. So A goes to DA, B goes to DB, C goes to DC, and R goes to DR. Well, what do we get? We get DA, DB, DC divided by 4 DR. And if you collect all of the D's, this is D cubed ABC in the numerator divided by D times 4R in the denominator, otherwise known as D to the 1. And if I have a D cubed and a D to the 1, then they cancel each other out, and you're left exactly with D squared, right? Because D to the 3 divided by D to the 1, you do 3 minus 1. So what you end up with is exactly D squared times ABC over 4R, right? And this is exactly what we want, that the area is multiplied by D squared. Okay? So this is our first hint that this is a reasonable formula, right? If I multiply all of the length inputs by D, it does get multiplied by D squared. So it acts the way an area formula should, right? If I just said that the area of a triangle was ABC, you would be able to tell me no, can't possibly be the case, because if I multiplied A and B and C all by D, then that formula would get multiplied by D cubed, and that's no good. Okay, you need that your formula gets multiplied by D squared if you multiply all of the length inputs by D. Because it's an area formula, area is two-dimensional, so you're going to have D squared. Okay, so this is just another example of what we did a lot of 2 weeks ago when we took all of these one-dimensional, two-dimensional, and three-dimensional formulas, and we saw how they scaled when you multiplied all of the length inputs by a certain thing. Will I use the square root on both sides to get the final answer? No. No, this is the final answer. It's not even a final answer. I'm just checking that this satisfies the properties that an area formula should satisfy. So it does. I'm going to prove the formula on a later page. This is just before the proof. This is just, okay, look, it looks like it could be an area formula. It's satisfied. It's basically of degree 2. All right. So any question? Okay. So let's actually prove this. Okay, so how do we do the area of a triangle in terms of the circumcircle? Well, the derivation first proceeds in 2 steps. So you first have to show that the area of the triangle is equal to 1/2 AB sine C, and then second, you show that sine of the angle C equals little c divided by 2r. Okay? And then if you combine these 2 steps, then it shows that the area is 1/2 AB sine C, but that sine C, this is sine of C, you replace this with C over 2R, and you actually get 1/2 AB times C over 2R, and that simplifies to ABC over 4R. Okay, so these two steps, we're going to call them step 1 and step 2. On this page, I'll do step 1. So if I have a triangle like this, let me draw the triangle a little bigger. If I have a triangle like this, okay, so I'm going to draw the angle C over here. This is going to be the angle A. This is going to be the angle B. And in this case, I have that B is going to be, let me actually, yeah, this is going to be B, and this is going to be A. And so the derivation over here is what happens when I draw an altitude of this triangle. If I draw an altitude of this triangle, well, if I look at the angle, oh, wait, it's blue. If I look at the angle C over here, well, what is the sine of C? I'm going to call this H. Okay. Well, what do I have? I have that sine of C, by definition, is equal to the opposite side over the hypotenuse. So that's going to be equal to H over B. Or you get that H. Oh, what did I just do? What happened? Oh, no. Sorry, my Zoom broadcast went away. Let me try this again. Okay. Try that again. Okay. So sine of C is equal to H over B, or in other words, H is equal to B sine C. Okay, so this H, the height of this triangle is equal to B sine C, and that means that the area, so the area is equal to, well, 1/2 the base times the height. It's a little confusing because the base here is A instead of B, right? So maybe I should have drawn A and B in a separate place so that the base could be B, but I think we're all okay with the base being A and the height being H. So the area is 1/2 AH, and since H is B sine C, this is the same thing as 1/2 AB sine C. Okay. Yes, this is a standard trigonometric formula for the area of a triangle. Okay, but I'm deriving it for you. I'm showing you why this is true. Okay, so this is part 1 of the derivation. We want to show that the area of a triangle is equal to 1/2 the product of two sides times the sine of the angle between them. And what this does is it follows right away just from base times height. You just have to write the height in terms of a trigonometric function, right? And the height here, you can do it in terms of the sine of C because it's going to be equal to the opposite side divided by the hypotenuse. Okay, so this proves step 1. And then in order to get the full formula, we just need to do step 2. We need to show that sine of C equals C divided by 2R. All right, so any questions before we move on to step 2? Are there any questions about step 1? How we get that the area of the triangle is 1/2 AB sine C? Okay, so let's do step 2. All right, so how do you do step 2? Step 2 is a little harder. So we need this proof that sine of C equals C over 2R. So I'm going to draw triangle again. We'll call this C, we'll call this A, we'll call this B. and I'm going to draw this circumcircle, right? I have to draw this circle that goes through all of the points of the triangle, right? So I'm going to draw the center of the circle. That's going to be here. I'm going to call this point O. And what I'm going to do is I'm going to draw the diameter that goes from, so how do I want to do this? Right. I want to draw the diameter that goes through the point A. I'm going to draw this diameter here, and I'm also going to draw, so this is going to hit the triangle at a point over here, which I'll call D, and then I'm also going to draw this line from D to B. Okay. So this doesn't look that great, but let me say, because I didn't draw the circle very well, let me redo this diagram. I'm going to redo this diagram because I want it to look more like a circle. So let me get rid of all this. I'm going to draw the circle first. Okay, I think that's going to make it a little easier. So if I draw the circle first, there it is. Okay, it's giving me a perfect circle. Okay, and then I'm going to draw my lines, call it A, B, let me do A, B, and C. Okay, let's call it like this. Okay, so this is going to be C, this is going to be A, this is going to be B. Okay, so this looks better. So now I've got a center of a circle that looks like this, and I'm going to draw the line A through the center of the circle that's going to hit at D. So this is D. This is going to be the center of my circle. It's O. And now I'm also going to draw this angle here. Okay. So what do I know about the sides? Well, by definition, these sides, the side opposite an angle is labeled by its lowercase letter. So this is side C, this is side B, and this is side A. Okay. And well, what do I know? Well, the circumradius is R. So the radius of the circle is R. So line O to A is R, and line O to D is also R. Okay. So now I need two facts. So facts. So the first fact is, if you know this from geometry, is that if I look at angle ABD, that this is equal to 90 degrees. Okay, this is because this is a diameter, and any angle inscribed in a semicircle is always a right angle. Okay, so I'll say it's 90 degrees because it's inscribed in a semicircle. Okay, so this is a fact from geometry that this angle has to be 90 degrees. I'll draw that in. That's 90 degrees there because it's in a semicircle. Second fact is that angle C, which is angle ACB, is equal to angle ADB. Okay, so if I look at this angle ACB, that's the same as angle ADB, right? And that's because they cut off, or I'll say both cut off arc AB. Okay, so both of these cut off arc AB. You have this arc AB over here. No matter what point you go, it's a theorem about circles that the angles are going to be the same. So ACB and ADB are going to be the same angle. Okay? Be the same angle. So what does this tell us? Well, it turns out, so what's the consequence? So sine of C, well, this has to be the same thing as sine of angle ADB, right? Because they're the same angle, right? So they have to have the same sign. And what is ADB? Well, this is in a right-angled triangle. So it's the opposite side from the angle divided by the hypotenuse of the right triangle. So this is equal to C, this is the opposite side, divided by the hypotenuse, which is what? Well, the hypotenuse is a diameter of the circle. the radius is r, that means that the diameter is 2r. So it's c divided by 2r, which is the hypotenuse, right? And so this is exactly what we wanted, right? We wanted that sine c equals c over 2r, and that's exactly what we get. And sine c is equal to c over 2r. So I'm just going to box this. Okay, and so this finishes the proof. Okay, this finishes the second step of the proof. We needed to show that the area of a triangle is 1/2 AB sine C. And secondly, you needed to show that sine of C was equal to C over 2R. So this second proof, which is a little clever, shows that that's true. Okay, so yeah, so that's what we have. So this gives us our final formula that that the area of a triangle is given by ABC over 4R. Okay, so I don't remember who asked me about this, but the reason I did this is because somebody asked this question last week. So, and it's not a question you can treat quickly. It's a somewhat involved derivation. So I wanted to be able to do it in enough detail so that we could see why it's true. Okay, so this is why it's true. This is why the area of a triangle is equal to ABC over 4R. Remember, if you go back here, these are the two steps, right? First, 1/2 AB sine C. And second, you have to show that sine of C is C over 2R. And when you substitute that in, you end up getting this final formula, ABC over 4R. All right, any questions? Okay, all right, no questions. Let's move on. Okay, so that's all I want to say about geometry now. Okay, good. So I want to move on to today's topic, which we won't actually have that much time for, but we'll continue it next week, which is solving equations and word problems. So I think no one here, we're all math teachers or have been involved with math, will dispute that one of the most important and fundamental mathematical skills to learn is how to solve an equation. Okay, and a lot of times equations come in the form of a story called a word problem. And word problems are not the most technically advanced part of mathematics. It's not calculus, it's not trigonometry, it's not logarithms and exponentials, it's not combinatorics, it's not number theory. It's, I think a lot of us think of word problems as maybe a little bit more basic than that. But I will say, at least from my experience with American students, and I would guess it's probably true with Liberian students also, that word problems is one of the first things that your students will have lots and lots of trouble with. Okay, it's going to be one of the first things, even if they've been good at math up to this point. When they're encountering word problems, often a lot of people start to lose the thread. Okay, it's when they start not being able to do things consistently. And in my mind, this is the difference, right? The difference between somebody who basically gets math and somebody who doesn't is, are they able to set up and solve a word problem? Okay? If you can take a story or a model or something and translate it into mathematics and solve it, then you know the basics of how to use math to do things, to apply to things. If you can't do that, then it's very hard for you to be using math in any serious way. Okay? So I think to me, it's a very, very crucial point in your students' education that they're able to do word problems. Because that basically, if you can do word problems, you have a facility with manipulating math and using it to do the things you want to do. Whereas if you can't, then maybe you can do some arithmetic and you can memorize some formulas and you can solve some equations, but it's going to be very hard for you to ever put that to any practical use. Okay, so this is a big, big, big point for me that I think teaching word problems is one of the things that will make the most difference to your students in terms of will they be able to use math later on in their lives or not. Okay. So, a lot of what we're going to discuss today is in chapter 3 of The Art of Problem Solving, volume 1. I posted this on the WhatsApp thread back in September, but I'll try to remember to post it again after today in case it's gotten lost in the thread. But chapter 3 is all about equations. Specifically, it's about linear equations, so not very complicated equations. But it does have a section on word problems, and it has a lot of exercises at the end of the chapter about word problems that they start off pretty easy, and then they can get very tricky as you move on. Okay? So I want to spend some time practicing word problems because again, I think it's one of the most important skills that your students can learn is how to translate a story into mathematics and solve it. Okay? So that's going to be today's topic. So, what is the setup for word problems? So I think as far as teaching word problems goes is that you have to have a method. You have to have a method. When your students are seeing word problems for the first time, they're not going to know what to do. It's going to look completely different from anything they've ever seen in math, and it's going to be difficult for them to solve them without some kind of method. Okay? So you have to set up a systematic way, for approaching them. Okay. And what is the systematic way? Well, there's different textbooks do different things. The one that I learned, which I like, is called Keska. Um, sorry, what did I do here? It's called Keska. You may have your own way. You may have a book that has your own way. I'll teach this way because I've learned it, but I'm not going to say it's the only way, but I think it's a good way. So it stands for key, equation, solution, check, answer. Okay, it's Keska there. So what is the key step? The key step is you write down what are your variables and what quantities they correspond to. Okay? Maybe everything is in terms of one variable. Maybe there's more than one variable. Okay? So then you have the equation step. This is maybe the most important step. I'm gonna put some exclamation points here. This is probably the most important step is the equation step because you have to set up equations relating the variables. This is how you're really modeling the situation that you have in your word problem. Solution step, you solve the equation. For a linear equation, that's usually pretty straightforward. And then in the check step, which is optional, but we'll do it today, you plug in your solution to the original word problem to make sure that it's correct. Okay, so it's good to check your answer. So you plug in your solution to the original word problem to make sure it's correct. And then finally, once you're done that, you have your answer. Okay, once you've checked it and it works out, then you have your answer. Okay, the answer is not really a step. Okay, and so again, you may have your own method that you prefer or that your own textbook uses. That's completely fine. Okay, we'll use Keska today, but you can do it however you want. But it's important that you teach your students a method. Okay, because word problems can look very, very different from each other, but at least at the high school level, they can basically all be solved with this method. Now, the equations that you get may be more complicated for some problems than for some other problems, but at the very least, the method is consistent and will always work. Okay, and I think if your students know that there's a method that's always going to work, then they'll be more confident. Okay, so let's do an example. So this is a basic example. This is the kind of problem I've seen people send me on WhatsApp. Hey, Mr. Andrew, can you solve this problem for me? Right? So this is a standard example. So Aaron is 3 times as old as Bob. In 5 years, Aaron will be twice as old as Bob. How old are Aaron and Bob today? Okay, so I'm going to do this very carefully. So I'm going to start with key for Keska. Well, usually what you want to do is you take a letter. So I can say, let X equal Aaron's age. And now we have two choices for the key. I could either just say let y be Bob's age. These are the two letters, and I have two variables x and y, and I could relate them with equations. Probably a good way to do that. Or I could, let me do that first, okay? So let's say if I let x equals Aaron's age, why am I not? Oh, sorry, what's going on? Let x equals Aaron's age, and I'm going to let y equal Bob's age. Okay, that's the key. One step done. So now what do we have for equation? And I'm going to say equations. Because in this case, we have two variables, so we're going to have two equations. Okay? Okay. So the first equation says Aaron is 3 times as old as Bob, right? So we should translate that into something involving x and y. Well, Aaron's age is 3 times Bob's age. So x should be 3 times y. That's what it means for Aaron to be 3 times as old as Bob. So here I have that x is equal to 3y. And then another equation, I have that in 5 years, Aaron will be twice as old as Bob. So what does that mean? So in 5 years, what's Aaron's age? Well, Aaron's age in 5 years is x plus 5. Bob's age in 5 years is y plus 5. And I mean, I'll just write this here. This is Aaron in 5 years. This over here is Bob in 5 years. Right? And well, what do we say? In 5 years, Aaron will be twice as old as Bob. Okay, so x plus 5 should be equal to 2 times y plus 5. Okay, so these are our equations. Okay, so James, this seems right. But the point is not just to write down the answer. The point is to try to see how would we do this in a systematic step-by-step way, right? So the equations are x equals 3y, that's the today equation. And then x plus 5 equals 2 times y plus 5. That's the in 5 years equation. Okay, questions so far? Okay. So let's do the solutions. So what's my solution here? Well, we have two equations and two variables. There's different ways of solving this, but since you have x equals 3y, I like to just do a substitution, right? If x is equal to 3y, I can substitute the first equation into the second equation. So I'm going to substitute x equals 3y into x plus 5 equals 2y plus 5. And what's that going to give me? Well, instead of x, I'm now going to say that I get 3y plus 5 equals 2 times y plus 5. Right? This 3y over here is x. Right? So 3y plus 5 equals 2y plus 5. And now you just solve this like a standard equation. 3y plus 5 equals, well, 2y plus 5 is 2y plus 10. Right? We distribute the 2. And now if I subtract 2y from both sides,
Gain 5.
exactly. So you're going to get that y plus 5 equals 10, and that's going to give you that y is equal to 5. And once you know that y is equal to 5, then x is 3 times y, right? So x is going to be 3 times 5, which is going to be 15.
15.
Exactly. Right, so you get James's answer, right? So what's the solution? The solution is Aaron is 15 and Bob is 5, right? Okay. That's what happens when you solve the equation. So you do a substitution that turns two variables into one variable, so you can solve it. And now let's check, right? So let's just check. Is maybe I'll write down the check over here. So check today. Well, what do we have? Aaron is 15 and Bob is 5. That's good, right? Because today Aaron is supposed to be 3 times as old as Bob. So let's check the next thing. In 5 years, Aaron will be twice as old as Bob. So in 5 years, what do we have? We have that Aaron, two A's in Aaron. Aaron is 20 and Bob is 10. And that's good too, right? Aaron's going to be twice as old as Bob in 5 years. So now we have our final answer exactly, which is Aaron is 15 and Bob is 5. Okay. So I'm not claiming this is a terribly hard problem, but I'm using it just as an example to illustrate these different sets for solving a word problem. And what I find for students mostly is that the solution part is not the hard part. If they're able to set up the equation correctly, then they will almost always get the solution correct. The much harder part for most students is being able to do the key in the equation correct. Once they can model the key in the equation correctly, they're usually pretty good at solving the equation. In any case, that's a skill they've practiced a lot, right? I mean, they've had, here's an equation, solve this equation, solve this equation, solve this equation. They've done examples of that. But the skill of modeling, of translating a word problem into math, that's something that they maybe have not done as much. And that's really these first two steps, the key and the equation. Okay, any questions on this example? Okay, great. Okay, so let's do another example. So a little more difficult example, not too bad. Car drives from Monrovia to Kakata at 50 kilometers per hour and then back to Monrovia at 30 kilometers per hour. What is the car's average speed during the trip? Okay. And if you say 40 kilometers an hour, you're wrong. Okay. So it's tempting to just say, oh, 30 and 50, the average is 40. That's got to be the average speed. But not going to be the case. Okay. So in order to do this, we need to actually set up. Let's do it carefully. Let's use the same method. Let's have a key, right? So the key, well, what variables do we need? Well, I told you how fast the car is driving. I didn't tell you what the distance from Monrovia to Kakata is, right? So why don't we make that a variable? Okay, so the key is going to be, I'm going to let maybe capital D is going to be the distance from Monrovia to Kakata. Okay, I use these two examples because these are the first two places that I went to in Liberia. Okay, so, all right, so let this be the distance. And we actually don't need any more variables. That's really the only unknown here, right? So we want to know what's the average speed during the trip. Well, we know that the average speed is that the average speed is equal to the total distance
Over the time.
over the total time. Exactly. Right? Total distance over the total time. Right? So what's the total distance here in terms of our variable? Be careful. So yeah, what is the total distance? Oh, so maybe I'll say I'm going to start this is going to be the equation part here. Okay, so now we're going to do the equation. The equation is going to be average speed equals, well, so what's the distance, right? You drive from Monrovia to Kakata and back. So if d is the distance from Monrovia to Kakata, then driving there and back is going to be 2 times d because you're doing a round trip, not a one-way. So the average speed is going to be 2d. That's the total distance, right? This is the distance. That's the total distance. Now divided by the total time. Now, how much time does it take? Well, if d is the distance from Monrovia to Kakata, let's say in kilometers, maybe I'll say, I can say it doesn't actually really matter, but I'll just say in kilometers. Okay. And you drive at 50 kilometers per hour, then the total time is going to be d divided by 50. So d divided by 50 is how long it takes you to drive from Monrovia to Kakata, but on the way back, you're only going 30 miles an hour. So the amount of time that it takes to get back is going to be d divided by 30. This is, I'll call it T1 and T2. Right? This is Monrovia. The T1 is how long it takes to do the first leg of the trip, and T2 is how long it takes to do the second leg. Okay. So now let's just try to simplify this. Right? So this is going to be 2d. We can look for a common denominator here. So we're going to get 30d. So the common denominator actually is going to be 150. So we're going to get 3d over 150 plus 5d over 150. Right? Normally I would write common denominator equals 150. I just don't have a lot of space. So I'm going to say that, right? But 50 and 30, our common denominator is 150. And so this combines to be 2d divided by 8d
Eight,
over 150. Right? James, yeah?
no, according to answer.
Okay, great. Oh, good. Yeah. Yes, that's going to be right. So now, what is that? Well, dividing by 8d over 150 is the same thing as multiplying by 150 divided by 8d. And so now we're going to cancel out the d's, and this leaves us with, okay, so I should really, now what we're doing is the solution. So this gives us 300 divided by 8, or in other words, 37.5 kilometers per hour. Okay. And take 37.5 kilometers per hour here. Okay, so it's interesting. You go out at 50 kilometers, you come back at 30. You might think the average speed should be 40, but it's actually not. It's actually 37 and a half. And the reason is you're spending more time driving 30 kilometers per hour than you're spending driving 50 kilometers per hour, right? Because if you're doing the same trip but slower, you're spending more time. So the trip back takes more time than the trip there. And that means that your average speed is going to be more weighted toward your slow speed rather than toward your fast speed. Okay. So the average speed here is going to be 37.5 kilometers per hour. Okay, so for this one, I'm going to skip the check for time, just for time, because I want to make sure we get to our next example. So I have one more example that I want to make sure we get to before we finish. But before we do that, are there any questions about how we did this? So one thing to notice is that I don't need to know what the distance is from Monrovia to Kakata, right? I can look it up, but it doesn't matter, right? The d's cancel each other out. So it's good enough to just keep a variable d there that eventually gets canceled out. So I think the distance is something, it's about 50 kilometers probably. I don't know exactly. But the maybe a little less than that. But in any case, I don't need to know that distance in order to answer this question.
So the 2D represent it 2 times the distance will cover.
Right, because, well, 2D is the distance that's covered, right? Because D is the distance from Monrovia to Kakata. But in the problem, we drive from Monrovia to Kakata and then back to Monrovia. So the 2D
Oh,
is the total
okay.
distance covered, when
Okay.
D is just the distance from Monrovia to Kakata. That's why it's important to write down what your variables mean, right? So here I wrote down that D is this distance. And so I know if that's what D means, then the amount of total distance I travel is not just D because D is for distance, but it's actually 2D because that's the relation to the variable I defined. All right, so we need to write 2D because we do a round trip.
Okay. Thank you.
Okay. And that's why if you're not carefully writing down your key, then you run the risk of making this mistake that you say, oh, the distance is D. And then you'd end up getting an answer that's half of the correct answer. You'd get 18.875 kilometers per hour, which is too slow. All right, questions? Okay, let's do one more problem before we finish. So here's an example with multiple variables. So this is one of these, they're sometimes called fence painting problems or tank filling problems. It's a style of problem that we see a lot. So Thomas and George paint a fence for 4 hours, after which Sarah starts to help them, and they all finish 2 hours later. If Sarah had not shown up, it would have taken Thomas and George another 5 hours to finish rather than 2 hours. How long would it take Sarah alone to paint the fence? Okay. So this is a kind of question that certainly many of us here may be a little confused by it. And certainly if your students see a question like this, they're going to be confused by it the first time. Okay. So a lot going on. It's not an E. You certainly can't do this in your head. Okay. The key is, how do you set this up correctly? And well, what we need is a key. Okay. And well, what should be our variables? Well, basically, Thomas has a certain amount of time it's going to take him to paint the fence, and George is going to have a certain amount of time it takes him, and Sarah's going to have a certain amount of time that it takes her. So we should just give these time. Give these names. Okay, so T is going to be equal to time for Thomas. Sorry, what am I doing? No, Thomas to paint the fence alone. And then G will be the same thing for George to paint the fence alone. And then last, Sarah, S will be the time for Sarah to paint the fence alone. Okay, these are going to be our times. All right. And so what do we know? I'm going to rephrase this. So in particular, and these are all going to be in hours. Okay. Okay, so these are all going to be in hours. Okay. So in 1 hour, Thomas paints 1 over t of the fence. George paints 1 over g of the fence. And Sarah paints 1 over s of the fence. Okay, right? Because if it takes Thomas, 6 hours, then he's going to paint 1/6 of the fence in 1 hour. Okay, so I claim this is all that we need for the key. Now we can set up an equation, right? So what does the first sentence tell us? It tells us that if Thomas and George paint together for 4 hours, and then Thomas, George, and Sarah all paint together for 6 hours, Thomas and George and Sarah all paint together another 2 hours, then they finish the fence. So that equation, I'm going to have to use another page. So that equation, so this is going to be equation. So the first equation says that for 4 hours, so how much do Thomas and George paint in the first 4 hours? Well, it's 4 times 1 over t plus 1 over g. So 4 times 1 over t plus 1 over g. And then plus another 2 hours where they're all painting. So that's 1 over t plus 1 over g plus 1 over s, that this equals 1 fence. Right? So this is, the first 4 hours. And this here is the last 2 hours. So this is how much of the fence gets painted in the first 4 hours. This is how much of the fence gets painted in the last 2 hours. And at the end, they finish the fence. Okay. Second equation, if Sarah had not shown up, it would have taken Thomas and George another 5 hours to finish rather than 2 hours. So they would have worked 9 hours total on the fence, just Thomas and George, to finish it. So that equation just says that 9, 1 over t plus 1 over g, is also equal to 1. Okay? So these are our two equations. And what do we want to solve for? We want to solve for s, right? The question is asking how long would it take Sarah alone to paint the fence? So we want to solve that equation. We have to solve it for s. Right? That's how long it will take Sarah alone to paint the fence. We got to solve it for s. Okay. So let's see how we can solve this for s. I have these two equations. They involve t, g, and s, and I want to solve it for s. So let me rewrite this equation, right? This is 4 times 1 over t plus 1 over g, and this is 2 times 1 over t plus 1 over g, and then 1 over s. So I'm just going to rewrite this as 4 times 1 over t plus 1 over g plus 2 times 1 over t plus 1 over g plus 2 times 1 over s equals 1. All I did was break this apart into 1 over t plus 1 over g and 1 over s. Or, in other words, 6 times 1 over t plus 1 over g plus 2 over s equals 1. Okay? So I have two equations here. I have 9, 1 over t plus 1 over g is equal to 1. Okay, so actually here I'm doing solution now. So let me do solution. So 9 times 1 over t plus 1 over g equals 1. That tells me that 1 over t plus 1 over g equals 1/9. Right, so I'll even write this over here. This tells me 1 over t plus 1 over g equals 1/9. So we're going to substitute 1 over t plus 1 over g equals 1/9. What happens when I make that substitution? I'm going to substitute in here. I have 1 over t plus 1 over g here. So what we get is 6 times 1/9 plus 2 over s equals 1. Well, 6 times 1/9 is 6/9 plus 2 over s equals 1. If I subtract 6/9 from both sides, I get 2 over s equals 1 minus 6/9 is 3/9, otherwise known as 1/3. And now I can cross multiply, and I get that s is equal to 6. Okay. So again, I'm going to skip the check. So this says that it takes Sarah 6 hours. So it takes Sarah 6 hours. Again, I'm going to skip the check. Sometimes the check is easier than other times. So in the first example, it was very easy to check. In this example, it's not quite clear exactly how you would check. So that's why I say the check is optional. The check is good to do if it's easy to do. Otherwise, you don't have to do it. You can just check your algebra. But the idea here is that we started with something confusing, but there are 3 different variables because we have 3 different people. And then in order to set up equations relating these variables, we had to use the 2 sentences that we were given, right? One is it takes Thomas and George together 4 hours, and then Thomas, George, and Sarah another 2 hours to finish the fence. That was this equation 4 times 1 over t plus 1 over g plus 2 times 1 over t plus 1 over g plus 1 over s equals 1. That's your first equation. And then the second equation is if it's just Thomas and George, it takes them 9 hours to finish. So 9 times 1 over t plus 1 over g also equals 1. And from that, the question isn't just saying solve the equations. The question is saying specifically, how long would it take Sarah alone to paint the fence? Okay? So it's not saying solve the equations in general. It's saying specifically solve for s. That is the variable that you want. There's 3 variables, but the question is only asking for s. In fact, in this problem, there's not enough information to determine t or g alone. So if you try to solve for t, you're going to wind up in trouble. But there is enough information for s. Okay, and that's what the problem is asking you to solve. So once you have your equations, then for your solution, you should be solving for the variable that you need. In this problem, it's just one variable. It's just s. Okay, and so then we get our solution there. Okay, any questions? Okay. All right, so if there's no questions, so we'll go. So here are the homework exercises for this week. So 3 word problems, and then one, is the standard make up your own problem exercise. So the first one, there's 16 bills in a pile. Some of them are $5 and the others are $10. If there's $105 total, then how many bills of each denomination are there? This is a pretty standard basic problem, not too bad. Number 2, find 2 consecutive odd integers such that 1/3 the smaller plus twice the larger equals 7 more than the sum of the 2 numbers. Sounds confusing when you say it, but if you just write down the key and write down the equation, you'll be able to solve it. The math is not going to be too hard. 3 is a bit more of a challenge. So 2 people starting at a point on a circular 1-mile racetrack walk in opposite directions with uniform speeds and meet together in 6 minutes. If instead they walk in the same direction, it takes the faster person 1 hour to gain a lap on the smaller one, on the slower one. So what are their speeds? So this one's a little difficult. I'll give it a star. It's harder than the other 2 problems. But in the end, you can do it with the same method. You can just write down a key. Probably your variable should be the first person's speed and the second person's speed. And then each of the 2 facts here is going to give you an equation relating those variables. And then fourth one would be come up with your own word problem and solve it using the full Keska method. And so in general, if you're looking for more, then if you look at all of the exercises in chapter 3 of The Art of Problem Solving, Volume 1, then there's something like 20 exercises. There's like 20 word problems, and they're very good. So if you want more practice, you can do all of the exercises there, or as many as you want to do. Okay, I'll remember to send out another copy of the book to the chat if you need to see this. Okay. So next week we're going to continue solving equations, and we'll also talk a little bit about inequalities. So that will be for our meeting next week on October 30th. So a final reminder to please type your name into the chat if you haven't already. We're going to start to be strict on enforcing data, enforcing attendance in order to continue receiving data. So we definitely don't want to miss your attendance record. Okay. Any questions? Okay. All right. So if there's no questions, I'll stop the recording.